My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics Webinar. Good morning to all here in Bangladesh, and a very good evening to all those who are watching this program live from USA. So today it's our 100th International Physics Webinar. So it's a very special day for our department and our university. Hope you are well and safe from Corona pandemic, and all we know that we are staying in a Corona pandemic situation. So we cannot continue our normal academic program inside the campus. So we have to start our online program. So our Department of Physics, Pabna University of Science and Technology has started its online program, including online classes and online international physics webinar. We have already completed our 99th International Physics Webinar. Today it's our 100th International Physics Webinar. So we are trying to adjust with this new normal situation. Today we are going to make a history for our department and university. It is a very important day for our department as we are going to witness such a great webinar with a Nobel-laureate in physics. As far as I know, this is going to be happened for the first time in Bangladesh, that in any international webinar has organized with the Nobel-laureate in physics. So I'm feeling proud for getting this opportunity. And it's my honor and privilege to host a Nobel-laureate in our international physics webinar. 2020, the year, is very important year for our country. Though COVID-19 has become epidemic, so this year we are celebrating the 100th birthday of our father of the nation, Bangabandhu Sheikh Mujibur Rahman, and this is also known as the Mujib year. So December month we are celebrating this webinar on December 4th. So December is also an important month of our country, as we know that we got our victory in the liberation war on the 16th December 1971. Bangladesh was born as the independent country on 16th December 1971 after a 9-month-long bloody war led by the country's founder, architect of the independent Bangladesh and father of the nation, Bangabandhu Sheikh Mujibur Rahman, in which 3 million people sacrificed their lives and about 0.2 million women were dishonored. So we want to dedicate this program to all those who sacrificed their lives of honor for independent our country. So today it's very important day for our department and our university. Today I'd like to welcome you all through a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics, University of Oregon, USA, in physics. And we have with us here today Dr. David J. Wineland, American Nobel-laureate physicist, the Nobel Prize winner in Physics 2012, Philip H. Knight, distinguished researcher, Department of Physics, University of Oregon, USA, connecting with us from USA through online. He has already connected with us, so I'd like to welcome our speaker. So good morning, sir, and good evening to your part, and welcome to our International Physics Webinar, and welcome our country and our university through online. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So it's my honor and privilege to host you in my International Physics Webinar. So for those who are new, I'd like to inform that we have divided our webinar into 3 parts. First of all, I'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion time. In that time, anybody can join with us, and you can also ask question by commenting. So you have already come to know the title of this today's 100th webinar, and the title is The Era of the Optical Atomic Clocks, and our speaker is Dr. David J. Wineland, American Nobel-laureate physicist, the Nobel Prize winner in Physics 2012, and Philip H. Knight, distinguished researcher, Department of Physics, University of Oregon, USA. And Dr. David J. Wineland received his bachelor degree from University of California, Berkeley in 1965, and his PhD from Harvard University in 1970. Following a postdoctoral position at the University of Washington in 1975, he joined the Time and the Frequency Division of the National Institute of Standard and Technology, then called the National Bureau of Standards, where he served as a leader of the experimental group working with trapped atomic ions until the end of 2017. His research focuses on quantum state manipulation of atomic and atomic-like systems with application towards quantum information, including quantum computing and quantum limited metrology. For example, in 1995, the NIST group demonstrated the first deterministic multi-qubit logic gates using individual quantum system. He holds a research associate position in NIST and adjoint professor position at the University of Colorado. David is a fellow of the American Physical Society and Optical Society of America, is a member of National Academy of Sciences, and has received on several advisory board and conference organizing committee. He has received several honors, including sharing with Serge Harouchi, College de France, Nobel Prize in 2012 in physics for manipulation and measurement of individual quantum systems. We can see this is the picture of Nobel Prize in 2012, and we can see his position, professional societies and committee. This is his Google Scholar ID, and his citation point is 63,564. So thanks for all of your patience. So before going to our speaker, I'd like to remind our previous webinar. So we have started our webinar on 21st June this year, and then so we have completed our 99. You can see our previous poster of our webinar. So we try to involve all the physicists from all over the world, and we want to make an environment for our students so that they can feel that it's like a classroom for them, and we want to give them opportunity to interact with the famous physicists. So you can see that all the physicists from all over the world. So, and today is very important day, and so that we are celebrating our 100th episode of our International Physics Web with the Nobel-laureate. This is 99th, and this is the 100th. So thanks again for your patience. So it's time to go to our speaker. So sir, thanks again for accepting our invitation. It's your time, sir. You can start your session, sir.
Okay, thanks, Pretam, and I guess good morning, everybody. So Pretam, maybe I lost my clock.
No,
on my computer. Maybe you could tell me when 10 minutes before the hour is done. Okay.
Okay, sir. Okay, sir.
Yeah, good.
Okay, sir.
Okay. All right. So I go ahead then.
You can, sir. Carry on.
Okay. Yeah. So just to summarize what I'll talk about then is first of all, why do we need precise clocks? And I'm going to give you a little bit of the basics of atomic clocks, and then explain why we want to go to optical atomic clocks. And I'm going to give some examples that are based on atomic ions, but there's a lot of good experiments also using neutral atoms. So, and I'll try to give you some idea of where the field is at, not just with ions, just where the best clocks are these days. And I'll give a little bit of personal, history, how I got in from when I was in as a young student in school, and how I eventually ended up in doing this kind of thing. So anyway, for centuries, one of the main application of clocks has been in navigation. And so in the old days, when the sailors would use their sextants and measure the angle of say a fixed star, say in the northern hemisphere, looking at the North Star, and measuring the angle between their level where they were standing, then they could tell where they were in terms of latitude. So the same idea was true for determining longitude, but because the Earth is rotating, then you need to know what time it is as well. So the basic idea is just the same, as long as you have time, so you can relate the angle to your position and longitude. And to give you an idea of how good time needs to be, if you, and the lower part of the figure there, I give a sort of error on distance d on the surface, and it's just given by, the radius of the Earth times the uncertainty in the angle, and of course that's given by, the angle is given by 2 times the frequency, that's one per day, times the imprecision of time. And just working out that little simple formula, you'll see that if we know time to 1 second, then the uncertainty in terms of longitude is about half a kilometer. So that's, and then to give an idea of how, oops, I should have, sorry, let me back up here. I just want to say that for good navigation, then in terms of longitude, we want very good time. And of course, these days the navigation is done by satellites, and the basic idea is pretty simple. It's a bit more complicated than what I'll say, but you can get the idea from this discussion. And the idea is that, first of all, you want to assume that you have a satellite and you have a clock that has a clock on it, and you have a clock on the ground, and they're synchronized. And so a simple protocol for finding the distance to the satellite is that you'll agree on some protocol, say the satellite emits a pulse of radiation on every second tick. Then there'll be a delay, and before that pulse reaches where you are on Earth, and that gives the distance just from the speed of the light times the delay time. And just to give an idea there of the errors that come into play, if we know time, if the clocks are synchronized to a nanosecond, then we can navigate down to with an uncertainty of distance of about 30 centimeters. And what that means in terms of the frequency stability we need is that it's essentially the same figure of merit, in this case 10 to the minus 14. We need a clock that's good, that holds its frequency to about a part in 10 to the 14th over 1 day. So, and of course, that was just the one dimension, and the idea of GPS, of course, is there's a network of satellites. And the system is somewhat overdetermined, so you can, the satellite, you can know the position of the satellites, and then by having several pulses coming in, you can do navigation in 3 dimensions. That's the basic idea. So what about clocks? And the clocks are, it's your simple notion of how they work is basically you have some periodic event generator, and then a counter, and then that gives you the time. And traditional periodic event generators that have first the rotation of the Earth, and then in the last century or so, pendulum clocks actually got very good, and so those are some of the best clocks were the pendulum clocks. And now what we're gonna use with our atoms is that basically the idea that atomic oscillations, say we have an electric dipole, and this figure on the right shows the oscillating electron density of this electric dipole. And the basic idea is then just the same, where we think about the pictures a little different. We think about superpositions of energy levels or oscillating wave functions, but the simple picture of an orbiting electron is pretty good for explaining how the clock works. And so the basic idea is that the frequency course is given by the energy difference between the 2 levels of a transition divided by Planck's constant. And one way we can observe this radiation then is in the emission mode, we say. And the basic idea is we have our atoms inside of some sort of cavity. Then we pick up the radiation that comes out, and we may amplify it, and then just count the cycles of the radiation. And this describes both a maser or laser. Just a little bit of history. Some of you may know that the laser or maser principle was first demonstrated in the microwave region, and that's why M stands for maser, and L, of course, stands for light in laser. But the basic idea is basically the same. So let's see. So just to give you a little bit of personal history. So I was in graduate school from 1965 to 1970 at Harvard, and my thesis advisor, he's just 2 people over from the right side of the trunk of the tree there in the background, and that's Norman Ramsey. He's probably one of the most famous atomic physicists in the 20th century. And actually, just to the left of Norman that's actually me trying to get close to the boss there. And so anyway, at that time, Norman and his colleague Dan Kleppner who then went to MIT, they had basically invented the hydrogen maser and demonstrated it. And basically, Norman wanted to have accurate measurements of the frequency of all 3 hydrogen isotopes. So my thesis was basically making a maser based on deuterium, and the only difference was the weight. The frequency is about 4 times smaller than that of hydrogen. And just so all of these in these hydrogen isotope systems, the basic transition is called the hyperfine transition. It's basically the energy. It's given by the energy difference, whether the electron and nuclear spin or oriented parallel or anti-parallel. That's the difference in the energy. And anyway, that you can see that number there is that's the frequency. The final frequency I determined for the deuterium maser. And, we want these oscillations, of course, to be very stable. And so one of the key things is we need to be able to control the environment. That is, all the things in the environment that can shift the frequency. That's sort of the name of the game. Whoops. So I described to you the laser maser method of operation, but typically what we do is rather look for absorption. So a simple example on the bottom there is we'll have some radiation source. We pass it through a container that holds the atoms, and we basically look for, one version is we look for maximum absorption with some detector, and when the absorption is maximum, then we know that the frequency of the oscillator source labeled F sub L is equal to the atomic transition frequency. So a simple recipe then for making an atomic clock is you have some oscillator on the left there. As a function of frequency, you can see above the box of atoms that there's an absorption curve. And basically what we do is we have some, I won't go into the details, but we have some simple electronic servo that allows us to guide the frequency of the source, F sub L, to be equal to F0. And then once we've achieved that condition, then we just count the oscillations of the oscillator to make our clock. And of course, for precision, we want a small range of absorption, given by this line width of this Lorentzian profile here. So actually, a more common mode of operation that certainly works. And in fact, some of the earliest and even some of the still operating clocks work on this principle I just described. But more typically now, and what I'm going to assume throughout the rest of this is that more common mode of operation is in the bottom part of the figure is we start the atoms in a lower energy state, and then we apply radiation for a certain amount of time, and basically then all we do is, and then after turn off the radiation, we measure the probability of the atom making a transition to level tube, and I think pretty clearly the absorption is maximum when the oscillator source is equal to the resonance frequency of the atom. So why atomic clocks? And there's a number of reasons, but I'll give you a flavor why we do atomic clocks versus other kinds in this view graph here. And I'm just considering a couple effects. But let's compare our atoms to a pendulum clock. And so one issue is environmental sensitivity. So one thing we have to worry about is the temperature of the system. In the case of a pendulum, the pendulum bob, given by the length L there, of course, it can change with temperature. And even for a very good material that has very low thermal expansion coefficient, say this coefficient being about 10 to the minus 8 per degree C, then the frequency sensitivity per degree C, we can easily calculate from the expression for the frequency of the pendulum. And it's a little lower than 10 to the minus 8 per degree C. For atoms, we have to worry about the fact that they're moving. And what comes into play there is one of the more interesting things that came from Einstein, and that is that time for moving atoms, time moves slower for them. It's not just that the oscillations slow down, time moves slower. And so we can account for that. And the little expression there in the middle gives the fractional frequency shift. And I've expressed that in terms for a given mass and temperature. For mass 133 it's about, that would be, say, example, it would be cesium. The frequency sensitivity is about a part in 10 to the 15th per degree C. So you can see that it's about 7 orders of magnitude less sensitive to temperature than the pendulum clock. Let's see. So what about reproducibility? And of course, there's a couple issues with the pendulum clock. One is that the length of the pendulum will depend on manufacturing tolerances and also the local value of G. And of course, the pendulum, the bearing holding the pendulum can wear out, and that would lengthen the pendulum. So there's all those practical issues. For what's nice about atoms is that basically, as far as we know, all atoms of a particular kind, say cesium 130, cesium 133, are exactly identical. And the other thing is the atoms don't wear out; they don't change their characteristics no matter how many times you drive their transitions. So in fact, just a little side note, many of you probably know that the definition, the international accepted definition of the second is based on the cesium hyperfine transition, which is about 9.2 gigahertz and so many digits. But if the definition is defined as being an exact number of oscillations of the cesium hyperfine transition. So why atomic clocks or optical atomic clocks? And one of the main reasons is for an optical transition, the tick rate, the oscillation rate of the electrons around the nucleus, let's say, depending on the transition, is just much higher. So basically, you can define any unit of time, say the second, into finer and finer steps by having higher and higher frequencies. And so that's one of the main advantages of using optical transitions. And of course, we want a very narrow absorption range. And one of the first examples we worked on was mercury 199, where the transition frequency is a little over 10 to the 15 hertz, and the line width, the absorption line width, was about 1.5 hertz, shown on the right-hand part of that figure there. So is using optical transitions a new idea? This is a little historical thing that's fun to talk about. And there was a text written by Lord Kelvin and Peter Tate, and they attributed this idea to Maxwell. And you can read the thing there. Basically, they're saying, that atoms just provides natural standards, and in the middle there, you see the time. They say the time of modes of vibration is known to be absolutely independent of its position in the universe. So basically, they had the idea of an optical atomic clock standard. One interesting thing about this quote is that they say, they have in here the phrase that it's absolutely independent of the position in the universe. And I'm going to show you later that that's not true, but they can be excused because they didn't know about Einstein's general theory of relativity. We'll come to that. So what about how do we play with our atomic ions? And basically, we call it a trap. We just make something that'll hold the ions in one place. And so I show an example of one ion in one of these traps. And so actually Hans Stamos and Wolfgang Paul shared the Nobel Prize in 1989 for the invention of these ion traps. Anyway, I won't have time to go into the details, but basically in this, what we use is called the Paul trap. It's a little different than there's another trap called the Penning trap. We use what's called the Paul trap after Wolfgang Paul. And basically we apply a combination of electric, static, and oscillating potentials. And we basically, with this arrangement, we make a three-dimensional harmonic wheel. And an analogy in 2D is shown on the left. It's just, you can think of it as a marble in the bowl there. So the experiments we started with were first on mercury ions, starting in 1981. And Jim Berquist, my colleague at NIST, was the leader of this project, but we worked together for the next 25 years on this experiment. Anyway, the idea is here we have our Paul trap holding a single mercury ion. It turns out the transition we're going to use is at the frequency that I showed you on one of the previous slides. It's in the ultraviolet, about 282 nanometers. And I label the levels with the atomic notation. If you're not familiar with that, it's just a label. But anyway, we use this transition in the ultraviolet as our frequency reference for the clock. And yes, well, in fact, we use one ion. The reason you might, why don't we put more ions in there? One of the things is that for mercury, for two ions in the trap, the upper state of the mercury of this transition, this clock transition, has a quadrupole moment, like football shaped distribution. And it turns out the inhomogeneous fields of one ion, electric fields of one ion acting on the other, they cause a frequency shift due to this interaction with this quadrupole moment of the. So basically, we want to keep it to one ion in the experiments, and that's what I'll talk about here. Again, this is just we have our clock transition at 282 nanometers. And how do we detect these transitions? And so it turns out there's another transition which in the mercury ion, it goes from the lower S level to a P level. And this transition has, the upper state has a very short lifetime. And so it can scatter a lot of photons up to 100 million per second. And if we just capture a very small number of those photons, we can easily do the detection. Because the idea is, let's suppose we started the atom in the ground state, and then we tried to make the transition to the upper clock level. And if the frequency was mistuned, it will remain in the ground state. So when we turn on this laser, then we'll see lots of scattering. On the other hand, if we are in resonance with the clock transition, it will make a transition. The ion will make a transition up to the upper clock state. And then when we turn on the second laser, we won't see any fluorescence. So we get essentially 100% detection efficiency on when the ion has made the clock transition. So just going on with these single ion experiments on mercury, I show this strong transition. And actually, one interesting thing is we can make pictures of these. Because this transition is in the ultraviolet, we can't see it with our eye, but we can use an ultraviolet sensitive video camera, and so that's a picture of a single ion. And in fact, the optics is not good. We can show by other means that that's actually the size, the wave function that describes the atom is about 500 times smaller than the dot you see in the picture. So the other thing we want to do is that I've talked about the time dilation shift due to motion, is we want to be able to cool the ions to suppress this relativistic time dilation. And it turns out we can use the radiation pressure from this transition. If there's time, I can. If there's time at the end, I can. This so-called laser cooling idea in this example here is fairly easy to describe, but it takes a few minutes, so I won't describe that now. But just to say, we can use this radiation pressure from this laser to slow the motion of the ion down. And we can, as I said, we can also use it. In addition, we can use it for detecting the ion, which level it's in. So a little background is here. When I went to Boulder at NIST in Colorado, my first task was they had just built a new cesium beam frequency standard. So my first task for about the first year or so was to just help get the thing running. And so that's a lot of my time was spent the first year. But the person that hired me there, his name is Helmut Helvig. He knew the importance of this, this idea of laser cooling. By the way, the idea came from when I was a postdoc with Hans Steenmelt. We had this idea of how we could do this cooling. Anyway, he was my group leader at NIST, was keen on supporting the idea of being able to see it. So he got us some money to try this experiment. And so in 1978, we were successful in doing the cooling. We first demonstrated it on a magnesium ion, and later on a mercury ion, the one I just talked about. And basically with this radiation pressure cooling, we could start it nominally at room temperature. That's the ion, that would be the temperature of the ions normally, because just given by the thermalization with some residual background gas in the vacuum system. But anyway, so the temperature would start at 300 Kelvin, and we could cool the ion to a temperature of about 1 millikelvin. So huge reduction in this second order, or the time dilation shift, almost a factor of 1 million. So anyway, that was what we did. And this is just a picture of the person I did the cooling with is Bob Drollinger there on the right. And then Jim Berquist is the person working on the Mercury ion clock, and Wayne Atano there was doing a lot of the theory and for the experiments. And anyway, that was our group in 1979. So anyway, I'll say a little bit just to kind of conclude. There's a lot of steps went in between. We started this in 1981. So basically, the kind of advantages we realized with the system is, first of all, the trapping means that the average velocity of the ion would be 0, and that would get rid of the so-called first-order Doppler shift. Laser cooling then substantially reduced the time dilation shift. And there were some other features. We put the trap in a liquid helium environment, and that was basically to avoid two things: the fact that collisions with background gas would heat the ions. Basically, any background gas is frozen out on the vacuum container walls. And also another interesting effect is that at room temperature, the black body radiation, just the thermal radiation, the electric fields from that is kind of interesting. They're at around 10 microns, but they're about 10 volts per centimeter, the electric fields from the thermal radiation. So anyway, but after many years of work, you can see there's almost 25 years. Basically, Jim's, with Jim and his team, they were able to measure the Mercury transition with an uncertainty, systematic uncertainty of about 7 parts in 10 to the 17, and that was the first time that the uncertainty below that of cesium was achieved. And so that kind of, you might say, I don't know why you say it set the stage, but it was the first experiment where we could do better than cesium in terms of the systematic uncertainty. And just to briefly say, there's many other ions which are of interest. There's, excuse me, I list some there, and of course I mentioned neutral atoms. They're very good. And this reference I show on the bottom is a little bit out to date, but if you can quickly mark it down, it covers basically all the different kinds of clocks. So it's a good reference to start with. So anyway, we have to correct for many things. I haven't mentioned, for example, we have to worry about the ambient magnetic fields, and that'll shift the frequency of these transitions, and we have to calibrate the magnetic field so we can calculate out the shift from the magnetic fields. I've already mentioned the time dilation due to atomic motion. We can express that to a very good degree by laser cooling. There's another interesting effect that also from Einstein, and that is the so-called gravitational potential redshift. So in Einstein's general theory of relativity, what he showed was a clock, the frequency of a clock will be shifted if it's in different gravitational potentials. And I showed the expression on the right-hand side. And it's basically another version of a time dilation shift, in this case due to the gravitational potential. So just to give you an idea the size of these things, suppose, just a little story here, suppose you and a twin were separated at birth, and let's say you live at sea level and your twin goes to live in Boulder, Colorado, which is about 1.6 kilometers above sea level. It turns out after 80 years, your twin will be about a millisecond older than you. So it's a very small effect, but because the accuracy of our clocks these days is so high, we can see this. So just a little fun demonstration we did a couple of years ago was that, so basically we actually switched to aluminum ions after mercury. They had a few properties that were a little bit better. In any case, the principles are just the same as we realized from mercury. Anyway, this shows a picture of our single ion single aluminum ion clock, and you can see there's a lot of optics involved, and so it's not a very compact device. But anyway, we could get very high precisions with this setup. And what we did for fun, we had a reference clock in an adjacent room. It was actually just off to the right of where this picture is taken, and the tables of the height of the ion traps above the floor were the same in both rooms. And so when we measured the frequency, we could basically measure to extremely high precision that the ratio of the two clocks was 1. And then just for fun, what we did was that this is James Chow, and you can see one of the main people working on this, and you can see he's put jacks underneath the table on our first clock, and he raises it up, in this case about 33 centimeters, and we could actually see this frequency shift from this gravitational potential redshift as shown on. So the clock, when we raise the first clock, it actually runs faster because it's in a weaker gravitational potential. Anyway, so what about the future? And so one of the things that we still think about the application, even at these extreme precisions, we still think about doing navigation. And one of the things people think about is navigation at, say, about the 1 centimeter scale. And one application people think about is maybe we can measure the Earth strains. That is, we could either do it with timing or with this gravitational potential redshift. We can get down to this level, and this might these strains on the Earth. That is the height, the relative height of, say, 2 positions, maybe a kilometer or 2 away from each other. That would be a strain if they shift differentially, and that might be people think that might be a precursor, at least, or maybe a predictor of earthquakes. There's many fundamental things we think about, and one thing we've done a few tests on is we've made clocks, say, out of mercury and aluminum and other atoms, and they depend differently on the basic forces, particularly electromagnetic versus strong forces. And if the ratio of these forces changes in time, we should be able to measure that, or at least and what we've done is put limits on the rate of change of the so-called constants of nature in time. And several experiments around the world have been done similar to that. People now have thought of ways to use the accurate frequencies of clocks to do gravity wave detection. And also, a sport for ever since I've been a student is maybe we can find deviations from Einstein's general relativity, and that hasn't happened yet. So he's safe. And the other thing, actually, more recently, people come up with ways to, at least for certain models of dark matter, to possibly detect dark matter. So those are some of the fundamental science applications. And let me say, I'm embarrassed I can't go through all these things, but what this view graph shows are several groups around the world that are working on different clocks, both ions and neutral atoms, and that paper, the Reviews of Modern Physics paper I showed you before that, they're in there. So this view graph is a little bit out of date, but the basic idea is we hold our ions. In this case, I show a different kind of trap, so-called linear ion trap, where the ions are lined up in a string. In the neutral atom guys, they can make a 3-dimensional trap, or excuse me, an array of 3-dimensional traps. It's called an optical lattice, and basically they've now gotten down to the point where they can put one atom in each of those spots of the array. You can think of it kind of like a 3-dimensional egg crate. But anyway, the one nice thing about the neutral atom experiments is that they work with much larger numbers. I say we've been working with 1, and one of the limitations there is that in the lower right hand, that we want larger numbers because it takes less measurement time to reach a certain measurement precision. And in fact, the time it takes goes as 1 over the number of atoms, the square root of the number of atoms. So by increasing n, we increase the measurement precision. And so we need to do that with the neutral atom guys are already working on the order of 1,000 atoms, and we need to start working with more to decrease this measurement time. And so one idea, I show a reference for one idea, but many of the ion labs are pursuing it. Anyway, I show just a few examples on this view group, but there's many more groups around the world working on both ions and neutral atoms. So I'll say a little bit about my personal story, how I got into this. And so my parents grew up during what was called the Great Depression in the U.S., where the economy was in horrible shape from 1930 to 1941. And my parents were lucky because they both had jobs. And but anyway, because of this, because they knew the devastating effects of didn't have a good job. I mean, they certainly emphasized for me to get a college education, and that was the first order, was just to be able to find a good jobs. And so they basically they stressed that they wanted me to keep good grades in school. The other thing is my father was good even when I was very little. He encouraged mathematics, just playing simple games with me concerning math. But I must say my parents were very supportive. They gave me a lot of freedom as long as I kept up my grades. There was a lot of freedom to explore. And so when I was younger, it was model airplanes, and I still do that to some extent. But basically, that chose me at age 11, and I was always interested in mechanical things. So with my buddies, even when we got to be teenagers, we were all crazy about cars and motorcycles. And I actually got my first car when I was 14. I couldn't drive it until I was 16, but my father helped me get it and bring it home. And sort of in those 2 years, I tore it down and fixed things and built it back up. So that was my first experience with cars. And so I continued this through high school. And so this shows a picture of me and my friends modifying a 1936 Ford. And I think the one thing is, you could say there's just a lot of goofing around, but the one thing I wanted to say is that, working with this group of guys, it's very much like working in a physics lab, where you're in almost all cases, you're not working by yourself. Most people are working in groups. And so this experience of working, with the guys on our cars was very much like the way we work in our labs in groups. So just to say a little bit, after high school, I went to the University of California. My first 2 years, I went to the University of California at Davis, and it was more a bit of a convenience. It was close to where I grew up in Sacramento, California. And so anyway, but Davis was a good school, but it was primarily agricultural. So midway through, or after 2 years at Davis, Berkeley was sort of the school for physics, and so I basically transferred down there for my last part of my undergraduate education. And it turned out it was very easy to do, since it was in the University of California system. I didn't have to do anything. I just had to choose different classes. I could easily move down to Berkeley. So that was a very simple thing to do. And of course, then I went to Harvard, and then to NIST in 1975. And so I basically was at NIST for 42 years, and only recently have gone to the University of Oregon. But so this shows the NIST team around a little bit after I left the NIST to come to Oregon. But you can see we expanded from 4 people to almost 30. I forget how many. I forgot to count in this paper, but we got up to over 30 people at some point. And it was regular staff like myself, maybe 5 of us who had regular positions, and then a number of postdocs and many students. We were only about 2 kilometers away from University of Colorado, so the students could easily come and work in our lab between, around class times and things like that. So, and the other thing I want to say is that one thing of being at NIST was that I had great leadership. The one person we all liked her name was Catherine Gebbe. She was director for about 25 years, and everybody liked her. And the one thing we liked about her was that basically her philosophy was very simple. She said, find good people, give them money, and let them go. So she was very good about that. And then later, that my director after her was has been Carl Williams, and he also has the same philosophy. So I think one thing to say is when I was in graduate school and as a postdoc, I had my heart set on going to a university job, but it turns out that I got a couple of offers, but they were at places that just couldn't give, didn't have enough support to get serious research going. So I was really lucky that I went to NIST because I had really good support. And we had NIST support for the first few years, and then we got a lot of outside support from various other government agencies as we went along. And another thing about the whole experience was that you got to know a lot of good colleagues, friends along the ways. And this shows a picture. So that's me on the right, next to my wife, and then Serge Haroche and his wife Claudine. And I got to know him in the early '80s, and it was it was real nice. It was nice to be able to share the prize with him. What's interesting, it turns out that his experiments, ours, you could say, roughly speaking, we're using light to measure atomic properties, and his experiments, very simply, he's using atoms to manipulate the states of light, the photons in the cavity, and so they were kind of complementary things. And what's interesting, a lot of times when we'd write down a Hamiltonian for our system, it would, for these two, the ion experiments and his cavity experiments, they would look exactly the same. So the basic physics had a lot of the same features. And anyway, it's a fun experience to share that with him. So just maybe a bit of advice, and it sounds kind of trivial maybe, but I think that the best advice I can give is find something you like and then just go for it. That I think you have to find something you like, because if you don't like it, you're not going to stick with it. And I think if you like it, the real reward will be, especially in research, the real reward will be that you get to do very nice demonstrations and cool experiments, and I think it's very satisfying. That's satisfying, and that's the real reward. I certainly wouldn't go in any field for the money. Particularly in physics, you're never going to be a millionaire, and so I think But I think anyway, all I would say is, even if you change out of science, you want to like what you're doing, and if you don't, you're just it's not gonna work. Anyway, with that little note, I will conclude, and thank you for listening. Thank you.
Sir, for your wonderful presentation, and thanks for sharing your story, life story with us. So I think our students have benefited lots, so if you allow, we can start our discussion.
So should I maybe I'll escape out of this and then go to the.
Yeah.
Okay.
Yeah, you can stop share. So yeah, you can see. So we have got some guest with us, and we have got some question in the Facebook and YouTube. So if you allow, we can connect our guest with us, and we can read the question.
How do I clean up the screen so I just see you and the other people? Pardon?
Okay. So okay, I just manage. So just stop share.
Yeah,
maybe you need to stop share.
I actually stop screen, but not,
okay, I'll
there
do
we
that.
go.
I'll
okay,
do that.
Okay, thanks.
Yeah. Okay. So we have a guest from India, Harsh Yadav. So can you listen, Harsh? So I think you have muted your.
Not on. Can you hear me?
So
no.
Could you? Yeah,
okay.
no, not you. The guest and the Harsh Yadav. So. Okay, so I can start reading the question before going to guest. So the first question: does the atomic clock work precisely near 0 Kelvin? I can add the question in the screen.
So I see the question. Yeah. So I mean, the answer is yes. I mean, One simple reason we talked about in my presentation, and that is that you can suppress the time dilation shift, and there's other reasons. It's not you don't have to be exactly 0 Kelvin. There's no particular advantage for that, but operating at very low temperatures does help in a lot of ways. And I mentioned two is one is that we even though we work the traps are in high vacuum, there's still some background gas collisions, and at low temperature, even 4 Kelvin, any background gas is frozen out on the walls. And the other thing I mentioned was that the black body radiation shift, it goes as temperature to the 4th power. So by going to very low temperature, we can almost completely suppress that effect.
Thank you, sir. We have another question. So according to the concept of time dilation, higher velocity and gravity can slow down time and change the shape of the space. The slowdown rate can be measured using atomic clock. So my question is, can higher velocity and gravity affect the functionality of?
Well, I mean, the answer is yes. Higher velocity leads to a higher time dilation shift from from the motion, and gravity can shift the frequency as well. I would say that though that I think that, for example, on the effect of gravity, for clocks on Earth, they all have about the same gravitational potential redshift. So if they're nominally at the same height around the say the surface of the Earth, we tend not to see it because it subtracts out the same way from all the different clocks. But certainly the velocity, having higher velocity is an issue that we have to take care of.
Thank you, sir. We have another question. So what reference clock is an atomic
yeah, that's a good question. So we basically have to, it's kind of a bootstrap process. We make more than one clock. And in fact, the ideal situation is to have 3 clocks, because if let's say one is fluctuating more than the others, by having 3 clocks and intercomparing, you can tell which one has the biggest fluctuations. And then the job then is basically to do the detective work to figure out why it's fluctuating. And I think that's certainly part of the game. I mean, this is most of the time what we do is try to figure out why frequencies are fluctuating and things like that. So that's how we spend most of our time, in fact. But anyway, the answer to your question is basically we just need to intercompare clocks to get an idea.
Thank you, sir. We have another question. So what element do clock use?
There's a whole range now, and I listed some examples. I mean, you can almost go to many places on the periodic table. So as I say, the best clocks for a long time were the Cesium clocks, and actually the first clocks on Cesium were made in the mid-50s, and it turned out for up until about 2005. That was, about 50 years, it was the best clock. It was partly because, a lot of people working on it, trying to figure out what causes shifts and things like that. So finally, as I mentioned there briefly, in 2005 was the first time where any other clock had done better than the existing Cesium, and that was this mercury clock. Anyway, I could go through the table, but there's many elements. I forget the number. There's probably 15 elements that work fine.
Okay. Great. So this may be the similar question. So why do atomic clock use only Cesium? Maybe I
think I've answered that. There's many others now that are better than.
Yeah. So thank you, sir. There is another question. What is the?
Okay, it's basically I think I explained briefly with hydrogen. So the energy difference of the transition, the lower energy, I forget which way, but it's basically one of the states has the electron spin and the nuclear spin aligned. The other state has the electron and nuclear spin anti-aligned, and those two states are different energy. And so that's what gives the energy difference divided by Planck's constant is what determines the frequency in the case of hydrogen, and Cesium too, for that matter.
Thank you, sir. We have Another question: what is the exactly difference between the active and passive frequency standard?
Yeah, I think a good example is an active one would be, say, the maser or laser, which actually, it's radiating continuously. And the passive one, at least the way we usually use the term, it's one where it's not radiating. You're actually inducing transitions, and then, as I said, you're looking for the maximum absorption to determine the frequency. So that's the basic difference.
Thank you, sir. So how gravity affects time?
Well, I thought I tried to explain it. I mean, anyway, so I think the main thing is in terms of the clock world, it's basically this gravitational potential redshift, and on the surface of the Earth, it's an effect. It's about I may get this wrong. It's about a part in 10⁸. The shift, as opposed to if the clock was in outer space. And actually what's interesting that I just for fun, one time I calculated the gravitational potential redshift from the Virgo cluster, galaxy cluster, and it's about 50 light years away, but the shift is about 5,000 times larger than the shift of clock to the clocks on the Earth. So it's amazing to think about things like that. But in the case of the Virgo galaxy cluster, it basically the potential, across anywhere around the satellites around the Earth, it's basically the same. So it just subtracts out of. We don't see the effect, but still, it's a huge number.
Yeah. Thank you, sir. We have another question, sir. Since the atoms are always in vibrations, can we consider the matter as another form of bios?
I'm not sure what the bios means.
Okay. Then we have another question. We can go that question. So, does higher frequency mean more precision in clocks? If yes, so why is that?
Well, I think the simplest way to say it, and I did try to say it, is that basically, in terms of defining a time interval, say the second, if the oscillation frequency is higher, then you can divide up the time interval into smaller and smaller units. And so I think that's the main advantage of going to higher frequency. So that's just in terms of precision, and in terms of the what we call the systematic effects, the shifts like the time dilation shifts. I mean, that's a different issue. So it doesn't necessarily mean that they're better at higher frequency than lower frequency. That's a different issue.
Thank you, sir. We have another question. Is time zero inside a singularity of a black hole?
Oh boy, I don't think so, but I'm not the one. I'm not the one to ask about that stuff.
Okay, sir. So thank you, sir. As we don't have any more questions, we can conclude our discussion session, sir. So thanks again for accepting our invitation, and I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir, for accepting our invitation. So the main aim of our International Physics webinar is to motivate and encourage our students in this Corona pandemic situation. So we have successfully completed our 99, and today it's our 100th international webinars. We are very lucky that you have accepted our invitation. And so I think students have learned a lot of things about the optical atomic clocks, and they are very glad to know the story of your life. So thanks again for accepting our invitation, sir. So hopefully
Yeah, it was certainly my pleasure, and good luck to all the students with their studies.
Okay, sir. So if you say something for our students for the final times to motivate and encourage them. So
I'm sorry?
Could you say something for our student for motivate and encouraging?
Well, I think I gave my one little bit of advice there, and I think that's the main thing: is you certainly want to like what you're doing, or otherwise you just won't get very far. And I think there's no question that it'll take a hard work, but I think if you like it, it's not so much work. In fact, I've always thought, you know, for me, it's always been more of a hobby than a job. And it's one that I get paid at. So,
yeah, thanks.
anyway,
I think
the key thing is to you know, you want to find something interesting, and then don't hold back. Just, you know, do whatever you can to succeed.
Thanks, sir. So I think your parent also did a great thing that they give you the freedom, as you have mentioned. So that also a very important thing. So thanks again for giving us time, sir. I think it was a very great webinar and great day for our department. And so thanks again, and bye for today. So good night to your parts, and good night.
Good morning.
Yeah, good morning to here. So,
okay.
Thanks again. Bye.
Yeah, you're welcome. My pleasure.
Yeah.
Bye-bye.
It's my honor and privilege actually, sir, to host you in my international physics webinar. So thanks again. Bye, sir.